Example 2.5. A mole of an ideal monatomic gas goes along path 1,3 or path 1,2,3 as shown. Rank the internal energies and draw an energy bar diagram for both cycles. During the transition 1 to 3, what is the working, heating, and change in internal energy of the gas? C. Repeat the same process for transition 1, 2, 3. This example is very similar to example 2.2. The difference here is we make the mathematical calculations. For all the heatings, the workings, and the changes in internal energy. So now we really get into it. So note that we have, so what's given here is that we have 1 mole of an ideal monatomic gas. And that immediately tells us that CV is 3/2 R and CP is 5/2 R. So before we get started, let's rank the internal energies. So the first thing I want to do here is that I want to rank the internal energies. Now, the reason why we want to rank the internal energies is that it helps us to get a sense of what's going on. So note that I have 3 states, 1, 2, and 3. So the way we do this is that we use PV, which is equal to nRT, which of course is proportional to the temperature, which is then proportional to the internal energy. So if I look at this thing, I'm going to come in here and I'm going to say, okay, this is my state. I have 1, 2, and 3. And then I have to worry about the quantity PV, which in this case is going to be in kilojoules. So when you look at the pressure, note that that's in kilopascals, so that's why I'm making it kilojoules. So now I just got to multiply these two numbers together for each of these states. So here I go. So if I look at state 1, that's 5 times 2, that's 10. So I get 5 times 2, so that equals 10 kilojoules. If I go to point 2, you can see that's 5 times 4. So that's 20 kilojoules. And then if I go to state 3, you can see that's 2 times 4. So that's 8 kilojoules. So then this immediately tells me that the internal energy, just by looking at that, should be 2 is greater than 1, which is greater than 3. So now I know my rankings here. So I could see here is that as I go from 1 to 3, there's a decrease in internal energy. So now that I've ranked these things, the thing that I want to look at now is that I now want to set up my signs. Okay. So now the next thing that I want to do here is that I want to determine the signs of Q, work, and internal energy. So I'm going to, so if I come in here, I'm going to take my graph right here, and I'm going to set up a table. So I'm going to set up a cycle that goes what? It goes from 1 to 2, then it goes to 2 to 3, and then I have a cycle that goes 1 to 3. So now I have my heatings. So if I start to write this out, I have my workings, and I have my change in internal energies. Now remember, we did a lot of this already in example 2.2. So here I go. So what do I expect? What I expect here is if I go from 1 to 2, I'm going to keep constant pressure. So the work decreases by the gas, decreases the kinetic energy. So that has to be negative because in order for the gas to expand, it has to give up energy to the piston. So then we could see here that this guy along this path is then going to have to add energy. And in the end, I have more microkinetic energy in the system. So then the heat from 1 to 2 has to be added. Now look at what happens from 1 to 2. I go from a higher pressure to a lower pressure and the same volume. I know that there's no work here. And because there's no work, I have to decrease the microkinetic energy, so I have to take heat out, which I do. So in this case, we take heat out between 2 and 3. Now note, we've done this one before already. So here, because there's an expansion, that means that the gas molecules lose kinetic energy to expand it. And we already said that the internal energy at 3 was lower. And from example 2.2, we said that this was we're going to have to add heat in this situation. Okay, so again, this is the example that we did in 2.2. So I'm going to stick to that. So now let's go draw the bar diagram. So I'm going to determine the signs and draw a bar diagram. Remember, this is just to conceptually understand what is going on. So here we go. So I'm going to take path. It's going to go from 1 to 2, and then it's going to go from 2 to 3. And then I'm going to have, over here, I'm going to have path 1 to 3. So let's set this up here. So I know that I start off with the same internal energy at 1. So let's draw that. So I'm going to come over here and I'm going to say, this is my internal energy at 1. So look how I'm drawing this. This is the same internal energy. They all start with the same internal energy, 1. So now what happens? What happens here is that as I go from 1 to 2, I'm going to have a decrease in kinetic energy. Okay. Now look at the areas. Look at the area from 1 to 2. It's got to be bigger than from 1 to 3. So then I'm going to come in here and I'm going to say that this is how much work was done from 1 to 2. And look how it's negative. When I go through cycle 1, 3, because it's a smaller area, I have to have smaller work. So that has to be the work from 1 to 3. So now let's look at the heating. So I know that when I get to internal energy 2, I have to have an increase in internal energy. So I'm going to say that I've increased my internal energy by this amount. So this will be the internal energy at 3. So when I look at this, this means here is that the heat has to increase the total internal energy by 1. So the first thing it's got to do is it has to kill off the work. And then I have to add heat to this thing to then make it increase here. So when I'm looking at this, here's what you're seeing. This is the heat that has to counteract the work. And so this is the heat from 1 to 2. And then what happens next? As I go from 2 to 3, you're seeing here that I have 0 work right here. So then I know that there's a decrease in internal energy. And let's say that the internal energy decreases, let's say, by this amount right here. Okay, this is the internal energy at 3. And look at that, I put 2 right here. So then that means here that I have to eject heat. So look at that, I have 1, 2, 3. So I have to eject out how much? 3 squares of heat. And this is going to be the heat from 2 to 3. So there's my bar diagram for this situation. Now, if I go over to here, we know that the heat has to decrease the internal energy. So I get to this internal energy right here. Okay, so now what do I see? Heat has to be added to the system in such a way so if I decrease that by that, ooh, I'm going to run into trouble here. Because I have to decrease this, so the work 1 to 3 is not correct. So I got to be a little bit more careful here. So I got to decrease this, looks like by 3. And then my heat, if I increase this by 1, this will be the heat from 1 to 3 that I add. So then I could see that my scaling on this one is not good enough. I have to have more work. So if I have more work, I have to come in here and I have to modify this thing. So the way I got to modify this is that I have to have more work here. So I'm going to bring this all the way down to 4. Because that work has to be more from 1 to 2, has to be bigger than 1 to 3 here. So that means now I got to go change this heat. So if I go change this heat, then that means this guy's coming up to here. And then this heat has to come all the way up to there. So now if I draw this out, it looks like this. So now I've scaled it right. So there's my bar diagrams. So what we're seeing here is that we added heat here, not subtracted, added. So now that I have my bar diagrams, I'm now going to go in and I'm going to start calculating these things. So here we go. So now let's calculate. We want to calculate all the heatings, workings, and changes in internal energy. So let's go for it. So I'm going to start with the easy process, which is process 1 to 3. Okay, here's 1 to 3 here. So this is the one we're looking at. So here I go. So what I'm going to do here is that I'm going to paste my thing so I know exactly what I'm looking at. Okay. So in this case here, the first thing I got to do here is that I have to determine what I want to calculate is I want to calculate the work. So let's calculate the work 1 to 3. So if I do that, remember this is a negative area. So when I look at the work, note that there are two pieces. There's this piece right here. And then I have another piece right here, which is this. So that area here should be, so the work between 1 and 3 is going to be negative of the area. And again, that's because the gas loses energy. So this should be negative the blue triangle minus the little tiny rectangle. So picture-wise, I'm looking at like this. So here I go. So then the blue triangle should be the difference between what? So it's going to be 1/2. Then it should be the pressure difference between 1 and 3 and the volume difference between 1 and 3. And then the little rectangle should be the pressure at 3 times the change in volume of 1, 3. So if you look at this thing mathematically, it really looks something like this here. So it's going to look as 1/2 times the pressure difference between 1 and 3 plus the pressure at 3 times the volume change of 1, 3. So then I'm just going to pick them off. So remember, this is all in kilojoules. So then look what I'm going to do. I'm going to do minus 1/2. Nope, let me put the square. So I have 1/2. The pressure difference is going to be 5 minus 2. Now note that that has to bring in 10 to the 3 plus the pressure at 2 times 10 to the 3 times the volume change, which will be 4 minus 2 joules. And so when I look at this thing, I get minus 7 times 10 to the 3 joules, and this will be the work between 1 and 3. So now I have the work. Now let's go calculate the internal energy. So now what I'm going to do here is that I'm going to look at the change in internal energy between 1 and 3. So here's what we know. The internal energy is given by what? So the change in internal energy between 1 and 3 is given by the mole number, the heat capacity at constant volume times the change in temperature between 1 and 3. Now note, CV is equal to 3/2 R. So if I start to put this in, if I just write everything out, I'm going to get 3/2 NR T3 minus T1. But note, we don't know the temperatures. We know the pressures and the volumes. So if I write this out a little bit more, note that this will be NR T3 minus NR T1. And what you're seeing here is that we could see right away that right in here, we do not know the temperatures. So what we want to do here is that we want to convert this. And so what we're going to do here is that we want to convert to PV. And if I convert to PV, note that I'm just using the ideal gas law. So the ideal gas law then says that this should be 3/2 of P3 V3 minus P1 V1. So then I'm just going right off the table now. So here I go. So I got 3/2. And so what do I see here? I see that this is going to be 3 is 2 and a volume of 4. So this would be 2 times 4 times 10 to the 3 minus 5 times 2 times 10 to the 3. And this will be in units of joules. So if I compute that, I'm going to get minus 3 times 10 to the 3 joules, and that's going to be my internal energy between 1 and 3. So then from the first law, I could put this all together. Okay, so the first law says this now. So then the heat between 1 and 3, I'm going to use the first law to calculate Q13. So if I do that, this tells me then that Q13 is going to be the change in internal energy between 1 and 3 minus the work between 1 and 3. And you could see that this is going to be 3,000. Let me be careful. Minus 7,000, which then gives me plus 4,000 joules for the heat between 1 and 3. And as expected, heat was added. Now let's go to the other process. So now we're going to go through the process 1 to 2 and 2 to 3. So here we go. So now I'm going to start off with path 1 to 2. So the first thing I'm going to look at is that I'm going to paste this guy, and I'm going to put this over here. So if I look at that, I'm looking at the work between 1 and 2. So the work between 1 and 2, that tells me that the work between 1 and 2 has to be the negative area along this cycle here. And when I look at this thing, look what happens. This is this whole area right here. So I have to calculate that area right there of that rectangle. So if I look at this thing, this has to be negative times the pressure difference between 5 kilopascals and 0 times the volume change between 1 and 2. So if I look at this thing numerically, this will then be minus 5 times 4 minus 2 times 10 to the 3, and that gives me minus 10,000 joules, and that's going to be the work between 1 and 2. So then the next path that we're looking at is that we're going to look for the internal energy. So in this case, we're going to look at the change in internal energy between 1 and 2. Now, there's a couple ways that there's not a couple ways. I was thinking about the heat, but let's look at the internal energy. So if I look at the internal energy, we know that it depends on the temperature. So then this should be NCV times the change in temperature between 1 and 2. But if I put in the details again, we can use the ideal gas law to convert this right here. Remember, these are unknown temperatures. So I want to convert that. So then what I'm going to do here is that I'm going to use the ideal gas law trick. And if I do that, I'm going to convert these to pressures and volumes. So then this becomes 3/2, and look at the pressure of 1 and pressure of 2. So this should be P2, V2, P1, V1. But look that the pressure of 1 and 2 are exactly the same, right? So the pressure of 1 is the same as 2. So what I can really write is that I can come over here and I could really write this as 3/2 P1 times the difference in the volumes. So then I see that this is going to be 3/2. And then look at that. So I have a pressure of 5. And then times the difference of 4 minus 2 times 10 to the 3. But look what happens here. This cancels out with that 2. So this leaves me with plus 15,000 joules. And that's going to give me the change in internal energy between 1 and 2. So now the last one that I need to calculate is I need to calculate the heat between 1 and 2. Now, there are 2 ways to calculate this. One way, we could use the first law. So if you use the first law, that tells you that Q12 should be the change in internal energy 1, 2 minus the work between 1 and 2. And if we punch in these values, we have 15,000 minus 10,000, which then gives us plus 25,000 joules, and that's the heat between 1 and 2. Okay, that's one way that you can do it. Another way that you can do this is that you could use the definition of the heating at constant pressure. So if I look at heating at constant pressure, well, that's just the same as the heat at 1 to 2, which is then NCP times the temperature from 1 to 2. And so that means here, if I change this, this will be 5/2 of NR delta T12. But we know that this quantity can be written as P1 times the difference between these two. And if you compute this, look what you get. You get 5/2 times 5, and then I get the difference between 4 minus 2 times 10 to the 3, and then again, like we did last time, we could cancel that, and look at that, I get 5 times 5, so I also get plus 25,000 joules. There's 2 ways to compute the exact same thing. Okay, so now we're in the last process here, and this is process 2 to 3. So again, if I use this over here, what you're seeing here is that you could see that this is an isochoric process. So if when I look at the work from 2 to 3, we see that this is isochoric. So this immediately tells us that the work from 2 to 3 is 0. And we know that the heat must be negative. So because this is isochoric, we know that the change in internal energy must be exactly as the heat. So using the definition of the internal energy, this would be NCV, the change in temperature between 2 and 3. Again, we don't have temperatures. So if I do that little trick that we've been talking about, between 2 and 3, now note that the volumes are the same. So if I write this out, this will be 3/2 and then I'm going to have P3 V3 minus P2 V2. But again, V2 and V3 are the same, so I can rewrite this as what? 3/2 of P3 minus P2 times the volume at 3. So if I start putting in my numbers, I'm then going to get 2 minus 5. Look how that's important to get that number, times 4 times 10 to the 3. And when I compute that, I get minus 18,000 joules, and that's going to be the internal energy and the heat. You know, there's another way that we could actually look at this thing here. Another way to compute the change in internal energy 2 to 3 is the change in internal energy for the cycle, the full cycle, has to be 0. In other words, if I go along a closed path, so that means that the change in internal energy of the cycle, a full cycle, is then going to be the change in internal energy from 1 to 2. Then I'm going to go to the change in internal energy between 2 and 3, plus the change in internal energy from 3 to 1 should be exactly 0. So that means I get back to my initial state. So now what we want to do is that we want to go in and we want to solve for 2, 3. So if I solve for 2, 3, this should be the same as the change in internal energy from 1 to 2 minus the change in internal energy from 3 to 1. But when I look at this thing, my numbers then show me this. So note here, we got to be careful here. We didn't calculate from 3 to 1. We calculated from 1 to 3. So here, I would say, note, we calculated this guy, not 3 to 1. So there's an extra minus sign here. So when I compute this thing here, I then write 15,000 joules, and then I'm going to get minus, and then I put in a plus here, because that's what we calculated, and this is going to be 3,000 joules, and when you compute that, you get minus 18,000 joules for the internal energy between 2 and 3. And note that matches what we did right there. So now let's summarize. So in summary, what do we have? We have cycle 1 to 2, 2 to 3, and then 1 to 3. So if I look at my heating, this is going to be my heating in kilojoules. This is going to be my work in kilojoules. And this is going to be my change in internal energy in kilojoules. So if I put in my numbers, this is 25, 18, plus 4. And then if I continue to go along, this is minus 10, 0, minus 7. This is plus 15, minus 18, minus 3. So there's a reason why I wanted to summarize these. And I want to show you what I'm talking about. Now note, this right here is a single cycle. So if I look at this guy, look what happens. So what this says here, that if I go for the cycle I would then say that the net work and the net heat should give me the net internal energy as I go from 1 to 2 and then 2 to 3. So let's add these. So if I look at the net heat, this will be 25 minus 18. If I look at the net work, this is going to be minus 10 plus 0, or minus 0. And then if I compute this number, look what I get. I get that this is going to be 7 minus 10, so it's minus 3 kilojoules for the whole cycle here. And compare these two. Note that this guy right here and this guy are the same, as they should be.